What could carve a mile-long wound into the Utah desert and drive it nearly 1,000 feet, about 300 meters, into the ground? Why would a crack slice across the landscape in such a perfectly straight line that it almost looks machine-made from the sky? And how could something that resembles a gigantic earthquake fissure actually be connected to ancient lakes, buried algae, overheated rock, and petroleum so thick it eventually turned solid underground? At first glance, the feature locals sometimes call the Utah Crack feels almost impossible. The walls plunge sharply downward. The trench runs with eerie precision through barren terrain. From above, it looks like the earth itself split open. For decades, people seeing photographs of the fissure have guessed it must be a fault line, a tectonic rupture, or perhaps some giant collapse tied to deep geological instability beneath the Colorado Plateau. But the real explanation is far stranger and far more scientifically fascinating. The crack is not a fresh wound in the crust. It is the exposed trace of one of the most unusual hydrocarbon systems on Earth. The massive fissure is tied directly to gilsonite, a rare solid hydrocarbon found commercially only in the Uinta Basin of northeastern Utah. Scientifically known as Uinta-8, gilsonite is essentially petroleum that hardened underground after being injected into enormous vertical fractures millions of years ago. What appears today as a canyon-like crack is actually the hollowed-out remnant of one of these hydrocarbon veins after miners excavated the black resin from deep underground. The geological story behind it begins roughly 50 million years ago during the early part of the Cenozoic era, when the region looked nothing like modern Utah. Instead of dry plateaus and sagebrush desert, the area was occupied by broad freshwater lakes trapped inside a slowly subsiding basin. The Uinta Basin itself formed during the Laramide orogeny, the same mountain-building event responsible for uplifting much of the Rocky Mountains. As compressional forces pushed mountain blocks upward across western North America, portions of the crust between those uplifts bent downward, creating structural depressions capable of collecting enormous volumes of sediment. One of those depressions became Lake Uinta, a vast ancient lake system that persisted for millions of years. Rivers draining nearby uplands carried mud, clay, volcanic ash, and dissolved minerals into the basin continuously. More importantly, the lake also accumulated immense quantities of organic material. Algae bloomed in nutrient-rich waters. Tiny plankton died and settled to the bottom. Plant debris drifted downward into oxygen-poor sediments where decomposition slowed dramatically. That low oxygen environment was critical. Normally, organic matter exposed to oxygen decays completely and disappears back into the carbon cycle. But on the floor of Lake Uinta, thick layers of organic sludge became buried faster than bacteria could destroy them. Over immense spans of geological time, the lake bottom transformed into an archive of preserved carbon. Sediment continued piling on top, year after year, century after century, until the buried organic muds lay beneath thousands of feet, hundreds to thousands of meters of overlying rock. As burial depth increased, pressure and temperature rose steadily. This process slowly transformed the organic-rich sediments into oil shale, particularly within what geologists now call the Green River Formation. The Green River Formation is among the richest hydrocarbon-bearing rock units ever discovered. It contains staggering quantities of kerogen, a waxy organic precursor to petroleum. Under increasing heat, kerogen breaks apart chemically through thermal cracking. Long hydrocarbon chains fragment into smaller liquid and gaseous molecules. This transformation effectively turns buried organic material into petroleum. But petroleum generation creates a major geological problem. Hydrocarbons occupy space, and deep sedimentary rocks are often relatively impermeable. As oil and gas accumulated inside the Green River shales, pore pressures began rising dramatically. Water trapped inside the sediments also heated and expanded. Eventually, the pressure became so extreme that the surrounding rock could no longer contain it. At that point, the basin essentially experienced a natural form of hydraulic fracturing millions of years before humans invented industrial fracking technology. When fluid pressure exceeds the strength of rock, fractures suddenly propagate outward. The pressurized fluids force the rock apart mechanically, creating cracks through which more fluid can escape. In the Uinta Basin, Hot water and hydrocarbons began hydrofracturing surrounding formations, opening vertical fissures through the crust. These fractures were not random. Their orientation reflected the regional stress field affecting the basin at the time. Most gilsonite veins trend northwest to southeast, indicating the crust was being stretched in a consistent direction. Under tectonic stress, rocks preferentially fracture perpendicular to the least compressive force. Once fractures initiated, fluid pressure drove them farther upward and outward like gigantic underground wedges. The process was remarkably dynamic. Pressurized water likely surged first because it flowed more easily than thick hydrocarbons. That water pulse weakened the rock and enlarged the fractures. Then came the heavier petroleum fractions. Unlike ordinary liquid oil trapped inside porous reservoir rocks, the hydrocarbons feeding the gilsonite veins were extraordinarily viscous. They behaved more like molten asphalt than free-flowing crude oil. Because the material was so thick, it could not migrate efficiently through tiny pore spaces in surrounding rocks. Instead, it concentrated almost entirely within the fractures themselves. The petroleum forced the cracks wider as more material entered under pressure. In some places, the veins expanded to widths of more than 10 feet, roughly 3 meters, though many averaged only 3 to 6 feet wide, or about 1 to 2 meters. The resulting structures resembled vertical hydrocarbon dikes cutting through the basin. Geologically, they functioned almost like igneous intrusions, except instead of magma injecting upward through cracks, the fractures filled with liquid petroleum. Over time, conditions changed again. As hydrocarbon generation slowed and temperatures gradually declined, the petroleum trapped inside the fractures cooled and solidified. Volatile compounds escaped or chemically altered. What remained hardened into a brittle, shiny black substance rich in carbon and nitrogen, gilsonite. This transformation produced one of the rarest geological deposits on Earth. The scale of the vein system is extraordinary. More than 70 identified gilsonite veins cut across the basin in parallel swarms extending over roughly 60 miles by 30 miles, approximately 100 kilometers by 50 kilometers. Some individual veins stretch for more than 14 miles, or around 22 kilometers. Others descend vertically for nearly 2,000 feet, about 600 meters, beneath the surface. Viewed in cross-section, these structures look astonishingly unnatural. They appear as narrow black walls slicing straight downward through layered sedimentary rock. Because the surrounding formations remained relatively flat-lying, the vertical orientation of the veins became even more dramatic. It is almost as if giant sheets of hardened petroleum were inserted directly into the earth. The geological mechanism responsible for this geometry remains one of the most fascinating aspects of gilsonite formation. Normally, hydrocarbons migrate through porous sandstone reservoirs or accumulate beneath impermeable cap rocks. But in the Uinta Basin, pressure conditions and petroleum viscosity combine to produce fracture-controlled emplacement instead. The hydrocarbons essentially invaded the crust mechanically. That process explains why the modern fissure exists at all. When miners discovered gilsonite during the late 19th century, they quickly realized the veins could be excavated directly. Gilsonite required no refining or smelting. Unlike metal ores buried diffusely through rock, the material existed in concentrated vertical seams. Fresh gilsonite could be broken apart with simple hand tools because it fractured easily. Early mining operations followed the visible surface traces of the veins. Wherever erosion exposed gilsonite at the surface, miners dug trenches downward along the fracture. Instead of tunneling horizontally through solid rock searching for ore, they simply followed the hydrocarbon seam itself. This produced long, narrow excavations resembling giant cuts across the landscape. The mining geometry mirrored the natural structure of the veins. Since the gilsonite bodies were steeply vertical, the excavations also descended vertically. Workers progressively removed the solid hydrocarbon while leaving surrounding rock walls exposed. Over time, the excavated trenches deepened dramatically. Some operations eventually transitioned underground using shafts and drifts. But many early mines remained essentially elongated open fissures cut directly into the earth. The modern Utah crack is the remnant of one of these excavations after decades of weathering, collapse, and erosion widened the opening further. The astonishing depth, nearly 1,000 feet or 300 meters, reflects the original vertical continuity of the gilsonite vein. Miners simply followed the hydrocarbon downward until extraction became impractical or the deposit narrowed. Seen from the air today, the trench appears almost surgical in its straightness. That precision comes directly from the geological fracture guiding the vein. Natural hydrofractures created under uniform stress conditions tend to propagate linearly because fluid pressure concentrates at crack tips. Once established, the fractures continue extending along the path of least resistance. The crack therefore preserves the geometry of an ancient petroleum plumbing system. What makes the system especially unusual is that the fractures remained open long enough for enormous volumes of hydrocarbons to enter before sealing themselves naturally. In many hydrofracturing environments, cracks close once pressure dissipates, but the viscous petroleum inside these fractures effectively prop them open. Eventually, the hydrocarbons hardened, locking the fracture geometry permanently into the rock record. In a sense, the gilsonite veins are fossilized fluid pathways. Even today, geologists debate details of exactly how the veins evolved. Some researchers argue that multiple pulses of hydrocarbon injection occurred over extended periods. Others suggest rapid emplacement events driven by episodic overpressure release from deeply buried source rocks. Evidence exists for both interpretations. Certain veins contain complex internal banding that may record repeated injections of petroleum. Some fractures appear to branch or merge, indicating changing stress conditions during emplacement. Nearby sedimentary rocks also display signs of localized deformation caused by fracture opening. In places, the surrounding formations were bent or displaced slightly as the veins forced themselves wider. The thermal history of the basin also played a major role. For kerogen-rich rocks to generate sufficient hydrocarbons, burial temperatures had to rise into the so-called oil window, typically between roughly 150 and 300 degrees Fahrenheit, around 65 to 150 degrees Celsius. Too little heating would leave the organic material immature. Too much would destroy liquid hydrocarbons entirely and produce mostly gas. The Uinta Basin occupied an ideal thermal range for generating thick petroleum fractions capable of solidifying later into gilsonite. Geochemically, the material represents an intermediate product between conventional crude oil and solid asphaltic hydrocarbons. Its chemistry explains many of its unusual physical properties. Gilsonite contains relatively low sulfur compared with many natural asphalts. It is also enriched in nitrogen-bearing compounds and resinous molecules. These characteristics give it high solubility and make it useful industrially in inks, varnishes, drilling muds, and asphalt modification. But those same properties also reveal clues about its geological evolution. As hydrocarbons migrate and mature underground, lighter compounds tend to escape preferentially. What remains becomes progressively richer in heavy carbon-rich molecules. Gilsonite represents an extremely evolved hydrocarbon residue. It is essentially the hardened remnant of petroleum that lost much of its volatile fraction over millions of years. Oxidation further altered the material near the surface. Fresh gilsonite can appear glossy and glass-like, almost resembling obsidian. Exposure to air dulls the surface gradually into a weathered matte black. The material becomes brittle and fractures conchoidally, much like volcanic glass. This visual similarity helped fuel misconceptions about the fissure itself. To non-geologists, the dark material lining parts of the trench looked volcanic or tectonic. In reality, it originated entirely from sedimentary petroleum systems. The broader tectonic stability of the Uinta Basin reinforces that conclusion. Modern seismic activity in the area remains relatively minor. No major active fault corresponds to the fissure. The crack does not continue widening due to crustal extension. It is essentially static, shaped primarily by erosion since mining ceased. Gravity continues modifying the trench slowly. Rockfalls periodically widen portions of the walls. Freeze-thaw weathering breaks apart exposed sedimentary layers during seasonal temperature changes. Rainwater occasionally channels through sections of the excavation, deepening localized erosion. Yet the overall structure persists because the surrounding rocks remain fairly competent mechanically. Much of the basin consists of consolidated sandstones, siltstones, and oil shales, capable of maintaining steep faces for extended periods under arid conditions. The desert climate itself contributes significantly to preservation. In wetter regions, such trenches might collapse rapidly through slope failure and vegetation growth, but northeastern Utah's dry environment slows chemical weathering and limits soil formation. As a result, the excavated vein remains visible decades after mining operations ended. The fissure therefore acts as a geological cross-section exposed directly to the sky. Standing at its edge is like peering into the plumbing system of an ancient petroleum basin. Each wall records millions of years of environmental transformation, lake deposition, organic accumulation, burial, hydrocarbon generation, fracturing, injection, solidification, uplift, erosion, and finally human excavation. Even the alignment of the veins tells part of the tectonic story. Their northwest-southeast orientation likely reflects stress redistribution associated with regional deformation following the Laramide orogeny. As mountain building waned and sediment loading evolved, differential stresses propagated through the basin. Those stresses governed fracture propagation pathways later exploited by pressurized hydrocarbons. In effect, the veins preserve a snapshot of ancient crustal mechanics frozen in solid petroleum. Modern extraction methods differ greatly from the earliest operations, but the geology remains unchanged. Contemporary miners still follow the same vertical veins underground, using pneumatic tools and careful excavation techniques. The deposits remain economically valuable because few synthetic materials replicate gilsonite's exact combination of properties. Yet the scientific significance arguably exceeds the industrial importance. The Uinta Basin gilsonite system demonstrates that hydrocarbons can behave mechanically almost like magmatic fluids under sufficient pressure conditions. It reveals how petroleum migration sometimes occurs not merely through porous rocks, but through catastrophic fracture injection events. It also provides direct evidence of natural hydraulic fracturing processes occurring on large scales deep underground. That realization has broader implications for understanding sedimentary basins worldwide. Many petroleum systems experience overpressure generation. Organic-rich shales commonly fracture under fluid stress, but few places preserve the resulting fracture networks so spectacularly or visibly as Utah's gilsonite veins. The basin essentially offers geologists a natural laboratory for studying hydrocarbon-driven fracturing processes in 3 dimensions. The fissure itself becomes more remarkable the more its origin is understood. At first it appears mysterious because it resembles sudden destruction, but in reality it represents gradual construction through geological time. Every stage required immense durations and precise conditions, millions of years of lake sedimentation, millions more of burial and heating, pulses of fluid pressure sufficient to fracture rock, hydrocarbon injection into newly opened pathways, cooling and solidification, uplift and erosion exposing the veins, and finally human excavation, revealing the structures fully. Nothing about it was instantaneous. Even the petroleum itself ultimately originated from microscopic organisms drifting through ancient lake waters 50 million years ago. Countless algae and plankton accumulated molecule by molecule until their buried remains transformed into hydrocarbons capable of fracturing stone. That chain of events gives the fissure its real significance. It is not merely an abandoned mine. It is the visible endpoint of a complete petroleum system operating across geological time. The crack also challenges how people think about oil itself. Petroleum is often imagined as underground pools or reservoirs trapped beneath cap rocks. The gilsonite veins show a very different behavior. Under extreme pressure conditions, hydrocarbons can become active geological agents capable of reshaping rock mechanically. The earth literally cracked open because fluids trapped deep underground generated enough pressure to overcome the strength of stone. Long before humans drilled wells or fractured shale artificially, nature was already performing similar processes on enormous scales beneath the Uinta Basin. The difference is that nature left behind solid evidence preserved in black hydrocarbon veins descending hundreds of meters underground. Today, the trench stands silent in the desert, stripped of most of the gilsonite miners once pursued. But the geometry of the excavation still mirrors the hidden fracture system created millions of years ago. The walls trace the path of ancient petroleum migration with almost unbelievable precision. For geologists, it is less like a canyon and more like an exposed diagram of Earth processes. Every layer surrounding the fissure contributes part of the narrative. The sedimentary rocks reveal the existence of ancient lakes. The oil shales record the burial of organic matter. The veins document hydraulic overpressure and fracture propagation. The solidified gilsonite preserves the chemistry of migrated hydrocarbons. The trench itself records the final human stage in the system's history. The so-called Utah crack, therefore, is not evidence of a planet tearing apart. It is evidence of how interconnected geological systems truly are. Ancient climate-controlled lake formation, lake chemistry governed organic preservation, burial drove hydrocarbon generation, pressure triggered fracturing, tectonic stresses guided fracture orientation, petroleum injection widened the veins, cooling solidified the hydrocarbons, erosion exposed the deposits, humans excavated them, weathering sculpted the remaining void. Each stage depended entirely on the one before it. That is what makes the fissure so scientifically compelling. It condenses an immense geological history into a single visible feature cutting through the Utah desert. What appears at first glance to be a simple crack is actually the exposed skeleton of a vanished petroleum circulation system born from ancient lakes in deep time. And nearly every inch of it was written long before humans ever arrived to see it.